Vector quantities also have a base unit known as unit vectors. So, one thing you have to worry about in this particular chapter is unit vectors. These particular axes which are traveling in their particular direction. That is, here it will be one direction for x, here it will be one direction for z, and here it will be one direction for y. This particular vector quantity is casting a shadow on the x-axis and it is going to cast a shadow onto the y-axis. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we are going to start a new chapter, that is motion in a plane. We discussed what is motion in a straight line. Now we are going to discuss motion in two dimensions, that is in the x and y axis combined. So we do know that there are three axes, x, y and z. Now we are going to deal with two-dimensional motions and its specialities. So without further ado, let's get right into it. So before getting into what is motion in a plane, we have to know some basic concepts which is necessary to understand motion in a plane. So the first concept is what is a scalar and what is a vector quantity. So we know or we discussed briefly what is scalar and vector quantities. So we discussed what was vector and scalar quantities briefly in the previous chapter, but we did not indeed actually fully disclose what vectors and scalars were. So we do know that vectors will have a magnitude as well as a direction. So vector quantities will have a magnitude plus that there will be a direction for that particular vector quantity, and scalar quantities will only have magnitude, that is a face value, but it won't have any particular direction. That was the definition we knew till date about vectors and scalars. But there is one more important thing that you have to remember, and that is vector quantities will only be vector quantities if they follow this particular law, and that particular law is law of vector addition. That is, if these particular quantities follow vector addition laws, then only these quantities will be known as vector quantities. They need to follow law of vector addition. Why this is so important? Because if we take the example of, let's say, electric current, we all know that electric current, that is electric current I is equal to Q by T. The flow of charges. If charges are flowing, we have to know that it is flowing in a particular direction. Let's say it is from A to B. So the important thing is that current is flowing from, or simply charges are flowing from A to B, which means there is a particular direction for that particular current to flow. It is from A towards B. So it has a particular direction, and current will obviously have a phase value. That is, it will have a magnitude 1 ampere, 2 ampere, maybe 10 amperes. So current will have a value and it is flowing in a particular direction. Does that make it a vector quantity? It seems it would almost make it into the vector category spectre, but in actuality it is actually a scalar quantity only because it is not following the law of vector addition. That is, even though this particular quantity has a particular direction and a magnitude value, this is not a vector quantity only because it is not following laws of vector addition. So in order for a quantity to be termed as a vector quantity, it should be following law of vector addition. And similar quantities such as force, momentum, acceleration, everything follows law of vector addition, or they will be added up vectorially in a given plane. But certain other quantities such as electric current, work, temperature, pressure, all these quantities are not added up vectorially, which means that they are actually scalar quantities. So one important thing you have to remember is that vector addition laws will be always followed by vector quantities, and these quantities which have a magnitude, which have a direction, which have to follow the law of vector addition is known as vector quantities. If not, they will be known as scalar quantities, and that is one thing you have to remember before diving into this particular chapter. Now, since the preface is covered, let's deal with some vectors and scalars that we take as examples for this. For example, examples of vector and scalar quantities. Let's say these are vectors and these are scalar quantities. So before diving into vector dynamics, that is how vectors actually function, we have to know which ones are vectors and which ones are scalars. For example, we'll start with the vector which we all know, that is force. So force, we know that force has to be applied in a particular direction and there will be a particular value to that particular force. Hence it is a vector quantity and also it follows the law of vector addition. And scalar quantity is electric current. So even though it has a direction, even though it has a magnitude value, since it is not obeying the law of vector addition, it is a scalar quantity. So another scalar quantity is temperature. We don't say what direction the temperature is shooting up. So we don't say what direction the fever is coming. It is not like, okay, the fever is 2 degrees to the left, 2 degrees to the right. We are just saying that, okay, it's very hot, it's 98 degrees Fahrenheit or 92 degrees Fahrenheit. Just like that, we'll say the amount of fever we are experiencing. Another quantity is pressure. We'll say 1 atm pressure, 2 atm pressure, not 10 atm pressure in the southwest direction, 5 atm pressure in the northwest direction. We don't specify directions for all these quantities. And so on, we can write on these quantities such as volume, area, and length, breadth. All these are actually scalar quantities because they only have phase values, only magnitude values, or they are not following law of vector addition, which these quantities can be added up as scalar quantities in a given plane. But vector quantities such as force or displacement or acceleration, velocity, momentum, all these quantities are vector quantities because they have a particular magnitude, a direction, and they follow the law of vector addition. Hence they are known as vector quantities, and if they are not obeying these laws, then they are known as scalar quantities. So since we have already seen a few examples of vector quantities and scalar quantities, let's dive right into vector dynamics or find out what exactly a vector is. So what exactly is a vector? We do know that if we put an arrow mark on top of any letter, it automatically becomes a vector. That is what we have been seeing around. So what is this particular arrow indicating? What is this particular arrow's purpose? So we do know that there is a magnitude value for a vector and there is a particular direction for a vector. This particular arrow is indicating that this particular quantity is having a direction, which means it is indicating that this is a vector quantity. So let's say this particular arrow is the arrow which is representing a particular vector. In this case, it is vector A. So this particular arrow is telling you that some quantity is being directed in a particular direction, and the length of this vector will give you its magnitude value. So if this is 5 Newton, then this will be the magnitude of a particular vector. Let's say vector A is equal to 5 newtons, then I can say that the magnitude value of this particular vector A, this length will give you that particular magnitude. And if I draw something such as vector B, which is equal to 10 newtons, then automatically the body will be growing. That is, the length of a vector which is having 10 newtons will be more. So remember, as you get more value, as the magnitude value increases, the length or the size of the vector also grows. Okay, the size of the vector also grows, and the direction of the vector is also important. If I draw a vector from left to right, then I can say that if I am referencing this particular frame, I can say that okay, this is going in the positive direction. If I draw one more vector in this particular direction, I can say that okay, these vectors can be added together with a positive sign because it is also in this particular direction. So these are both positive vectors. But if a vector is going in the opposite direction, then I can say that okay, I have to subtract this particular vector because it is relatively traveling in the opposite direction. So direction also matters, because as direction changes in physics, we use the negative symbol to indicate that particular change in direction. In this particular quantity, if both are going in the same direction, we can indicate that using a positive sign. If the direction is changing, it is going in the opposite direction, we will use a negative sign to indicate that particular change. And the relative size of that particular arrow, you can see that both these arrows is having relatively same size, which means they are two vectors having equal magnitude. So if two vectors are equal, vector A is equal to vector B, then this is how that particular vectors will look like. This will be vector A and this will be vector B. And if any vector is indicated as vector A is equal to negative vector C, it means that they are equal in magnitude. That is, the size is same, but the direction is actually in the opposite way. That is, these both vectors having same magnitude are now lying in opposite direction. That is, vector C is actually lying in the opposite direction. So direction is also important, and we can use a negative sign to indicate that particular direction with reference to the vector we are taking. So for example, this is in the positive direction and vector C is in the negative direction. So that is all about directions of vectors. And dealing with the more quantities, these particular vectors can represent many quantities which is moving in opposite direction. For a general example will be gravity. That is, acceleration due to gravity is always represented mostly in a negative sense, because it is always acting downwards. If a rocket is trying to go up, the gravitation, that is the acceleration due to gravity, is pulling on it, which means that the acceleration due to gravity is acting downwards relative to that particular rocket's motion, which means the rocket is trying to go up with a particular velocity, but gravity is pulling on it. The direction, the vector direction of that particular force being applied is down. So rocket is trying to go up. So up is positive and gravity is trying to pull it down. Hence that particular direction is taken as negative. That is how we take directional sense. We will see more examples, and obviously we will learn more about these directions along the way. But this is how we take directions and magnitude value of this particular vectors. So again, the length of the arrow will correspond or is proportional. The length of the arrow is actually proportional to the magnitude value of that particular vector. And for a vector, there are two quantities, that is the head part. This will be the head, this will be the head, and this will be the tail, or simply the body of that particular vector. So a vector will have a vector head and a tail, or simply the body of that particular vector, in which the length of that particular vector will be directly proportional to the magnitude value of that particular vector. So that is one important thing you have to remember. And the next thing is, how do we represent the magnitude value? So we actually represent the magnitude value. That is, magnitude value just means that we are disregarding any directional quantities. For example, if vector A is equal to vector C, then I can say that magnitude of vector C will be equal to just C. We are not considering any directions. We are not considering any directional properties of that particular vector. We are only considering the face value of that particular vector, and we are just writing that down. Then I can say that this particular quantity, which is now a scalar, that is without a direction, can be represented like this. And these two boxes is known as a modulus. So if any quantity, let's say this is vector A, can be written as modulus of vector A, then that means we are taking the magnitude of that particular vector, and the magnitude of that particular vector will be equal to this. That is, without the direction, without anything, without any directional properties, we are just writing down the magnitude value. That is why when certain equations are written down, instead of writing vector F, this is force vector, but sometimes we will only write down F. Then that means that that particular quantity only has magnitude. We are not considering the direction of that particular vector. We are only taking the magnitude value and not the vector component of that particular quantity. Here it is force. So if I write down force as F with an arrow on top of it, it is vector F. If I just write down F, it means that I'm just taking the magnitude value of that particular vector. Now just like every quantity, every physical quantity has a unit, right? We learned that length has a unit of meter, mass has a unit of kilogram. Just like that, every physical quantity has a particular unit. Just like that also, here vector quantities also have a base unit known as unit vectors. So one thing you have to worry about in this particular chapter is unit vectors. So just like we have centimeters, meters, or kilograms, grams, just like that, there is a particular unity or unit quantity that is represented for this particular vector also. Here it is a unit vector, that is, if I write this is vector A, then there is a unit vector quantity which is indicated by A caps. A caps is the unit vector of that particular quantity, and it is related to vector A by the magnitude of that particular vector into unit vector. That is, if I am writing down I have 5 kilograms of something, I am just saying that I have a magnitude of 5 times the base value of that particular quantity I am measuring. If I have 5 kilograms of banana or 5 kilograms of apple, I am just saying that 5 times magnitude value, that is the magnitude value is 5 of that particular base quantity, unit quantity I am taking. It is 5 into 1 kilogram. Just like that, here it is magnitude, here it is the unit. Just like that, the magnitude value, that is vector A, modulus of vector A, that is magnitude of vector A into unit vector, will give you vector A. So this particular quantity which has a roof on top of that is known as a unit vector, and this roof is known as caps, or simply this is known as A caps. A caps will represent unit vector. So again, if you just want A caps, we can also write it down such as A caps is equal to vector A divided by modulus of vector A. So if you divide that particular vector, any particular vector, by its magnitude value, then you will get the unit vector. It is simple. That is, it is basically saying that if you have 5 kilograms of something and you want to find what is the base unit of kilogram, then what is the unit value of kilogram, you're just dividing it by the magnitude value of that particular vector, then you will get 1 kg. This is unit value of this particular quantity. So just like that, vector A is divided by the magnitude of that particular quantity, then immediately you will get the unit vector. So this is one more thing you have to keep in your mind, that is all about unit vectors. Now one more quick thing, that is what happens if we multiply a vector quantity with a scalar number. That is, if I have a vector that is vector A, what happens if I multiply that with a certain number, let's say 5? What will happen? Will it be 5 into vector A, or will it be 5 times vector A, or is it anything different? Will anything happen to it? Well, the answer is that nothing will happen to it, because simply it will be 5 times vector A. The magnitude value will only increase, but no other changes will be there. That is, in general, we can say that if there is a scalar quantity lambda, and if you multiply that with a vector quantity, let's say vector A, then the resultant will be lambda vector A. There will be no other change. The direction of that particular vector will remain in the same way. The magnitude value will only be multiplied with that particular scalar quantity. So how this technically happens, I'll show you an example, but that will be later down the road, because if I show it to you right now, you won't be able to understand, but still if you want, I'll show it to you. So if, let's say, a vector A is denoted as 2i plus 3j, then I can say that if I multiply that particular vector with 5, then I can write this particular quantity as 5 into vector A will be equal to 5 into 2i plus 3j, or simply it will be equal to 10i plus 3 into 5, 15, 15 j. So there will be no other change, the direction will be still remaining there. There will be no other changes to that particular vector. It will be just multiplied just like that. What is I, what is j, and what am I just writing right now? I'll briefly explain it. Just I have given you an example for this, so we can come back and look at it again. So yeah, we are going on to the next thing, that is what is I, j, and k. So base vectors, or simply known as unit vectors. What are these unit vectors? So we do know that there is x, y, and z axes. That is, we have an x, y, and z axes. So what is this x, y, and z axes? X, y, and z axes are the three perpendicular axes which construct or which will help us explain this three-dimensional space to us. If you don't understand what is these three axes, just look at the corner of any room. One represents length, one represents breadth, and the other represents height. So with this, it will form a three-dimensional shape. Any three-dimensional shape can be thought out or traced in this particular three axes. So these are our world. That is, our three-dimensional world can be portrayed using these three axes. There is one more axis, that is the axis of time, but for now only we need x, y, and z axes. So just like I told you, every vector has a unit vector. Every physical quantity has a unit to it, like mass, kilogram, length, meter, just like that. These particular axes also have a base unit. So these particular axes which are traveling in their particular direction, that is, here it will be one direction for x, here it will be one direction for z, and here it will be one direction for y. So if we take the unit quantity, that is the base quantity of these three axes, we can say that those three can be represented as I cap, j cap, and k cap. So I cap, j cap, and k cap. I, j, and k are the unit vectors of x, y, and z axis. Earlier it was denoted as x cap, y cap, and z cap, but now every textbook has adapted the adaptation, that is, we will represent it as I cap, j cap, and k cap. So I cap is obviously for the x axis, j cap is for the y axis, and k cap is for the z axis. So like there is meter for length, kilogram for mass, and candela for luminous intensity, like there is base quantities for every physical quantity, these x, y, and z axes also have a base quantity. Here it is represented as I cap, j cap, and k cap. Why the cap? Because we just studied that unit vectors will have a cap. How do you find out unit vectors? It is vector, any vector divided by the magnitude value of that particular vector, then you will get the unit vector. And for x and y and z, it is represented as I, j, and k. Always remember, we are measuring it from left to right, that is I, j, and then k. If we measure it the other way around, then there is a problem in direction. We have to change the sign. Why that will happen, we will learn very shortly, but do know that if we measure it in the other way around, directional problems will arise. That is, we have to introduce a negative sign to that particular measuring. So always measure from the left to the right. How we measure the angle, always how we measure the angle, just like that we should measure these particular axes. That is, why that happens will be explained very shortly, but make it a habit, it will be good. So why did actually we learn about these x, y, and z axes, I cap, j cap, and k cap? Why are we learning about all this? That is because sometimes a vector may be needed, that is, a vector should be represented in its vertical and perpendicular components. But sir, what is this vertical and perpendicular components? That is what we are going to learn here today, that is components of a vector. So what is this components of a vector? We do know that there are two axes for now, that is the x and the y axes. So let's imagine that there is a vector, that is vector A, represented just like this. O is the origin. So let's say this is vector A represented as such. A can be anything. For example, it can be velocity vector, it can be acceleration vector, it can be displacement vector. It does not matter. The point is that a vector A is represented as such in a graph containing x and y axes. Then I am going to assume that this particular vector quantity is casting a shadow on the x axis and it is going to cast a shadow onto the y axis. So this particular quantity is going to cast its shadow onto the x and y axis. In theoretical terms, we can say that there will be a projection onto the x and y axis, but for you to understand very simply, I can say that there will be a shadow of this particular vector quantity along the x axis, and that will be somewhere around here. Okay, there is somewhere around here. And similarly, there will be another thing, that is another shadow casted onto the y axis, and that will be somewhere around here. So there are two shadows being casted, two shadows being projected onto the x and y axis. So what is these two shadows? How can we represent these two shadows? The magnitude value will be same, and here it will be along the x direction. So that is, the magnitude value will be same and it will be along the x direction, that is ax. If you want, you can also multiply the unit vector, that is ax I cap, and here it will be a y j caps. So there will be two components to this particular vector. Actually, in definition there will be three components if you are including the z axis coming towards you. But for now, for understanding this particular concept, let's imagine that here this particular vector is casting a shadow onto the x axis, and that is represented using ax I caps. And here, if it is casting onto the y axis, we can say that that is ay j caps. So there is an x component and a y component. Now how do we represent this particular vector? That is, how do we write down this particular vector in terms of its x axis and y axis components? So we can actually write it down as ax I caps plus ay j caps. Or simply we can also write it down as ax plus ay. Both are fine. This is more accurate, but this is also completely acceptable. So if a vector can be represented using its components, that is in the x and y plane, then we can say that these are the components of a vector, or simply this process is known as vector resolution. So this process of writing down a particular vector in the terms of its axes are known as vector resolution. In this particular vector, for this particular vector, I am writing down its vector components in the x and y plane. So x and y components. So I am writing it down in terms of the x axis component and in terms of the y axis component. Why this comes and why we have to write it like this is for mathematical reasons. That is, if we want to explain what are the forces acting on a particular object. Let's say an object is flying through space. If I shot a bullet and bullet is flying through a particular given space, I have to tell them that, okay, this particular object is traveling forward because it has a velocity in the horizontal component. That is, it has a velocity in the x direction. And it is having a height because it also has a velocity, or it has a perpendicular component in the y direction. That is why an object is having a height and still moving forward. So in order to explain all these quantities mathematically, we need these vector components. That is why we are actually studying these quantities, why we are representing it in the x and y components. So generally we can say that if there are three axes, that is, if there are three axes x, y and z, then we can generally write vector A as the perpendicular horizontal and the third axis component. That is, we can write it down as ax plus ay plus az. So we can represent this particular vector as the components of all three vectors also. So a vector quantity can be represented in terms of its axial components. In this particular case, it is y and x axis. So vector A can be represented as ax I caps plus ay j caps, or simply ax plus ay. So again, let's take this as an example term and simply write it down. So a vector can be represented as its x and y components. If there was a z axis, we will also write down plus az, but for now take it as an example and we can write it down as ax plus ay. Now this is the vector components of vector A in x and y plane, or simply the vector resolution of this particular vector A written down in its component form. And now we also learned that there is something known as a magnitude value. So magnitude value, I've told you what magnitude actually is, that is the face value, but I did not tell you how we can obtain it. So the way we can obtain it is that we can write down a root of ax square plus ay square. That is, if you take the modulus of vector A, what we are going to do is that we are going to square and add each individual component terms. Here there is only ax and ay, so that is why we put ax square plus ay square. If there was z term, then there will be plus az square also. So we will get the magnitude value of that particular vector. For example, let's say vector A, that is vector A is equal to 2i plus 3j. 2i plus 3j, that is the vector. Find the magnitude value of that particular vector and find the unit vector. That is the question. So what do? So first thing we have to do is that we have to write down in its ax and ay component, which means it is already written down. So here ax is nothing but 2i, because I is the unit vector of x axis, that is in the x direction, x axial direction, it is I, so it is 2i plus ay in the y direction it is j, so it is 3j. It is already written down. Vector A is equal to 2i plus 3j. Now we have to find the modulus or the magnitude value of that particular vector, and magnitude value of that particular vector is written down as root of ax square, that is 2i square. Don't have to worry about I, because this when squared will be equal to 1 and j dot j is also equal to 1. You just have to take this particular number. You don't have to worry about I, j, k and everything. Just take the particular value that is assigned. So if it is just I, it means 1 into I. So just take 1. Just like that, it is 2i. So just take 2. So it will be 2 square plus 3 square. 2 square plus 3 square, which is equal to root of 4 plus 9, that is root 13. 4 plus 9 is root 13. So that is the magnitude value of this particular vector. If you want the unit vector, all you have to do is that 2i plus 3j divided by root 13. That will give you unit vector A caps. Now why is it 2i plus 3j divided by root 13? Because we know that the definition of unit vector, that is A caps is actually equal to vector A divided by magnitude of that particular vector. And here vector A is nothing but 2i plus 3j, that is vector A is equal to 2i plus 3j, and magnitude value of that particular vector we just found out, that is root 13. So it is very simple. You write down vector A as it is and then you divide it by the magnitude value of that particular vector. If you want to be more fancy, you can just write it down as A caps is equal to 2i divided by root 13 plus 3j divided by root 13. So this is the unit vector representation of that particular vector A. So I hope it's clear and there is no confusion. So always remember, a vector can be resolved into its component terms, and generally we can represent vector A as AX plus AY plus AZ. So AX plus AY plus AZ. Those are the three component vectors in the X, Y and Z direction, and generally the magnitude value of that particular vector can be written down as AX square plus AY square plus AZ square. So for example, if we have a vector A is equal to 2i plus 3j minus 2k, how do we take the magnitude value of that particular vector? It's very simple. We take it as magnitude of vector A is equal to root of 2 square plus 3 square plus, always remember, plus minus 2 whole square. So it does not matter if there is a minus sign in this particular equation, because when squaring it will automatically become a positive value. That is why even if it is minus, plus, it does not matter, always take the square and it will be a positive sign. Just take the square, you don't have to worry about anything. Just take this number and square it. So here it will be equal to root of 4 plus 9 plus 4, that is 8 plus 9, that is root 17. Here the magnitude value is root 17. Just like that we can find the magnitude value, unit vector and vector components of any particular vector. This is how we represent any vector in its vector component terms, or simply this is known as vector resolution. So the very next thing we have to learn is two laws regarding vector addition. That is how we can actually represent two vectors, that is the resultant of two vectors. When two vectors are acting in a plane with a common starting point, or two vectors are acting in a plane, what will be the resultant? How can we find that particular resultant? For example, why do we need to find it? That is another question. So for example, let's say that there is one particular object where two people are pulling on it at right angles to each other. So they are both pulling with equal amount of strength. One person is pulling with 5 newtons of force and the other person is also pulling with 5 newtons of force. What will happen to this particular object? That is one question. Will it go in this particular direction or in this particular direction? If the forces were slightly different, we can say that, okay, since the force is very different, it will go in this particular direction or it will go in this particular direction. But now both people are exerting same amount of force. Where will this particular object move? So actually this particular object, let's say this particular object is being pulled in this particular direction and in this particular direction with a particular force, that is same force, equal in magnitude, different in direction. So where will this particular object move? It is found that this will move in between these two vectors and it will go in between those two vectors. That is, if one object is being pulled in two directions with the same amount of force, let's say with A and A with same amount of force but different direction, it is seen that the resultant movement of that particular vector will be in between, at an angle in between those two vectors, and this particular vector is known as a resultant vector. That is, the resulting motion or the resulting effect of that particular pull or push will be in between those two vectors, depending on the force applied, the angle, everything will be depending, but the thing is that the resultant vector will be in between those two vectors. That is, the force will be applied in two directions and the motion will be along this resultant direction. Regarding this, we have two laws, that is law of parallelogram vector addition and law of that is triangular law of vector addition. And the first one is triangular law or triangle law of vector addition, and what it states is that if two vectors can be represented as the two sides of a triangle, that is, if two vectors can be represented as the two sides of a triangle, then the third side taken will be equal to the resultant. That is, if two vectors are represented, that is, one vector is represented like this in this particular direction, another vector is represented like this in this particular direction, then the third side, that is this particular side, will give you the resultant of that particular vector. But one important thing is that while closing this triangle, make sure that you're not going like this, you're not going along the vector. You cannot draw an arrow towards this side. You have to always draw the arrow like this to the opposite direction. That is how vector triangular law of vector addition actually works. That is how the direction of that particular resultant vector will be. So that is why we represent the triangular law of vector addition and the sides as such. Two sides are represented as two vectors are represented as the two sides of a triangle, then the third side will give you the resultant. But remember, the direction of the resultant is taken so that it breaks that particular directional motion. That is, if one vector is like this, one vector is like this, you will have a tendency to draw it like this, but always remember it will be drawn in the opposite direction. So that is triangular law of vector addition. But similarly, we also have one more law, that is parallelogram law of vector addition. Again, if two vectors can be represented as the two sides of a parallelogram, then the resultant will be the diagonal. So the parallelogram law of vector addition states that if two vectors can be represented as the two sides of a parallelogram having the same starting position like this, then the diagonal drawn in between them will give you the resultant. And that is, if we have two vectors, let's say we have a vector A and we have a vector B, let's say that they are at an angle theta. Okay, let's say we have a vector A and vector B at an angle theta. Now, if these are representing the two sides of a parallelogram, then we can make it into a parallelogram like this. Then we can say that the diagonal drawn like this will give you the resultant of that particular two vectors. That is, if two things are pulling on some object like this, then the resultant will be in this particular direction. Now still, why is this has to be obeyed? Where does this parallelogram law come from? Everything will be soon explained. Just have patience. Just for now, know that there are two laws, that is triangular law of vector addition and there is parallelogram law of vector additions. Since we cannot directly add up vectors, that is we cannot directly add vectors like scalar quantities, we have to use these kind of laws in order to add vector quantities. Just like you saw in the before cases, that is vector A can be represented as 2i plus 3j plus 4k. No scalar quantity will be represented as such, because if scalars are represented, there won't be any directions. Since it is represented as such in terms of axes, components of axis, then we have to use these kind of laws in order to add them together. So I hope it is very clear that what is triangular law of vector addition, what is parallelogram law of vector addition, components of a vector, what a vector component is, what is a vector, what is unit vector, and equal vectors, what happens when a vector quantity is multiplied with a scalar quantity. I hope everything is clear and there is no doubts, because that is all for today's session. We will discuss more vector dynamics in the very next session. Thank you. I'll see you all very soon with a new and interesting topic about this particular chapter. Until then, thank you.